language there. Okay, so let's see. The mean household garbage in pounds per week is 27.854. Based on that data there, standard deviation is 12.923. I want to test the hypothesis that it is less than 30 pounds. That's what I want to do. That sounds like fun. So let's do that. I'm going to copy some data here. It's question number 1, but I'm perverting it into a new problem. Let's see, that doesn't slide. Can you guys kind of see those numbers? No, blow it up more. Let's try this. That's about, well, I guess I can go a little bit bigger. Whoa. Okay. That's about as big as I can make it, I think. So write down 27.854, or you could type in all of those numbers above. You take your choice. I'd recommend typing 27.854 is X bar, right? Is it a sample? Right, it's not all households. And then S is 12.923. Was it appropriate to take it to 3 decimal places here? Yeah, we usually go one more than the data. All right, I need to orient my board. Come on, there you go. Okay, so we are testing the hypothesis. So I'm giving you H1 or HA that mu is less than 30 pounds. What would the null hypothesis be here? Mu equals 30 pounds. And I'm going to go with a significance level of 1%. Draw a picture of the hypothesis and the significance level. And then we'll run our test and add to the picture. Less than 30, correct. Average weight of garbage in a week in pounds. Are we playing with Z's or T's here? T, wonderful. So the center of my distribution would be T equals 0 or mu equals 30. Because Mr. T is mean. Anybody ever remember what was that show again? The A-Team. Steven, what do you think about the A-Team? That maybe before some people in this class. Okay. So am I going to the left, to the right, or both sides here? Left? Excellent. Okay. So where does the point 1 go? Is that a point on the number line or a shaded region? Shaded portion. Excellent. So this shaded tail there, that shading part is the area in the tail, and that's 0.01. Beautiful. And we could, what's the number, the t-value that goes along with that called? Anybody remember? Critical t-value, yes, the critical value, critical t-value. So you need to do an inverse t on that. Now, not everybody has that on their calculator, so if this were on the test, you would be given that. Negative 2.46. Can somebody confirm that? Not that I don't trust Sean, but should always double check. Degrees of freedom would be 30 because we have 31 people in our sample, 31 households in our sample. So 30 degrees of freedom. Anyone else getting that? Yeah? Awesome. We can move on. All right. So this is all this information I've drawn so far is just the result of the null hypothesis, the alternative hypothesis, and the significance level. So what we're trying to find out is our mean 27.854 significantly lower, or is it just a little tiny bit lower? Right? Is it close enough to say it's the same, or is it far enough away to say it's different? Right? And that's what we're going to test next. So what's the shortcut button? Anybody recall on the calculator? It is a t-interval, right? So we're going to run a t-interval on the calculator. For anybody that prefers the old-fashioned way, does anybody remember the formula for the test statistic? No, that would be for a confidence interval. Yeah, the test statistic is it's like a z-score, but we use t stuff instead. Yes, almost. X bar minus mu. And then what? Over square, yeah. So if you wanted to do it the old-fashioned way, that would give us the test statistic. We're going to do the push a button on the calculator way. So everybody find your t-interval and see if you can enter the right numbers and see if we can get matching results. And the new Excel can do a t-interval, but it's a little different. Is that right, or is that a lie? Shannon, do you remember when we were talking about that in class the other day? Excel's version. Oh, I'll have to look it up again. Oh, it does not work. Yeah, it does something different. Yeah, it's a different thing. Okay, so Excel cannot do this like the calculator can. So where's that located on my calculator? I can't remember. Excellent, stats test. Okay, and we want the t-test or t-interval here? We're doing a confidence interval? Or are we doing a hypothesis test? Aha! Uh-oh. All right, we better review when we use which button. Who told me to use a t-interval? Oh, man, John, you're on my shit list. Okay. It is a t-test. So let's review. Let's make a little cheat sheet here for when you do what. Okay, there's two kinds of things we're playing with. We're either playing with proportions or we're playing with means. Right? Proportion or mean. Okay. If we're playing with proportions, are we going to mess around with z's or t's? Z's, correct. Proportions, we use z's. If we're messing with means, we use t's, correct. Okay. The next thing we have to decide is, are we doing a confidence interval or are we doing a hypothesis test for either one of these? Confidence interval or hypothesis test. So if we're doing a proportion and we're doing an interval, we have a single proportion, so it's a one proportion. Proportions use z's and then interval. So that's the shortcut button on the calculator. If we're doing a hypothesis test, then it's a one proportion z test. If you're working with means and it's an interval, then it's just a t-interval. If it's mean and you're working with hypothesis testing, then it's just a t-test that you would whip out. Another juicy bit of information here. When we're doing intervals, we focus on the data. So that would be p hat or x bar. That's the center of what's going on. If we're doing hypothesis testing, it's the null that's the center of what's going on, which would be p or mu, centers the distribution. So we switch our focus when we go from confidence intervals to hypothesis testing. We're just looking at it from a different direction. But it's a similar idea. So that's a cheat sheet for all the problems we worked on in chapter 7 and 8. You want me to give you that cheat sheet on the test? No. Don't write it on your hand or the brim of your hat. You can feel free to get that tattooed on a body part, though. Okay, so let's go back and do the right calculator button. We are doing a t-test on the calculator because this is a hypothesis test. Okay, so null hypothesis is what here? 30, yeah. X bar is the data. Let's, slide over to get that. 27.854-ish. S. Now, if you were to plug in these numbers to your calculator, you'd hit what to get all this data? One variable stats, correct. And would you be picking the sigma or the S for the standard deviation? The S, yeah. Most of the time we're going to pick S because we're running samples. And my S is 12.923. How many people do I have, or households? I have 31. That matters. And I am doing a left tail less than. And we're going to calculate that. Okay, so I get a t-score of negative 0.9-ish. I get a p-value of 18%. I'm always hoping if I want to reject the null that p is little. Little meaning like 1%, 2%, or less is what I hope for. Is p big here? Yeah. T equals negative 0.9. Let's see. So on my number line here, this is 0 in the middle. This is negative 2.46. So negative 0.9-ish is like right over here maybe. Negative 0.9-ish. The p-value is the area of the tail, in this case to the left because we're doing a left tail. We found that that area is about 0.18-ish, or 18%. So can I reject the null? Is 27.854 significantly less than 30? No, it is not. It's close enough. That if somebody said the actual mean of the population is probably about 30, we can say, based on our data, yeah, we can't refute that. We fail to reject the null here, correct? So fail to reject the null. Okay, which means we cannot accept that the mean garbage in a household per week is less than 30. So we cannot accept the alternative. Okay, so we can't accept that it's less than 30 pounds. So another thing I could say here is that my mean X bar, which is the 28 point something something, 546, 564, what was it? Oh yeah, 20, okay, there's the 8 in there. 27.854. Now you're really messing me up there, Sean. Oh gosh. Okay, whatever. Something like that. Okay, that is not significantly less than 30. Emphasis on the not. Significantly less than 30. That's what we found here. That's what I would tell my mother, that last part. She doesn't want to hear about nulls and alternative and reject and accept. She just wants the conclusion in plain English. So on the test, I want to know whether you accept the null or reject the null, and then I want a plain English sentence about what that means. I definitely want that from you, but then you're going to write me a sentence that my mom would like. Yeah, so you need to know whether you're rejecting. Now, it'll be pretty obvious to me from your sentence, I hope, after whether you reject it or not. What? Well, I wouldn't tell my mother that, but I'll tell you guys. I want you to write the formal and the informal. At the very least, you better write the informal. And if I understand what you wrote, then I should understand that you're rejecting or accepting the null. If you're not sure if you're clear, write them both down to be more clear. Does that help? All right, let's do another one. Let's see here. So we failed to reject. Oh, well, Taryn's not here. She said we don't fail enough to reject. She wanted to see one of those. Oh, I'm recording it for you. Hi, Taryn. Hope you're watching this in the future. All right. Ooh, outliers. How do we find outliers? We have two methods for outliers. Yeah, just let me get set up on my little page here. Oops. All right, I need to copy that. Control C. What? Wait, what? Okay. Okay, I need to see all this data to do this here. Okay, so what are our two ways of determining outliers? So, okay, so you're going to find, what's that called? Q3 minus Q1? Interquartile range. Interquartile range. So in this case, where are those guys? We've got this one minus that one, and I don't know if I can do that in my head. So what is 37.200 minus 18.595? 18.605, I'll buy that. All right, so that's the interquartile range. All right, and then what do I do with that? Okay, so then I take 1.5 times 18.605. Anybody with a calculator? 27.9075. Okay, and then we do what with that number? Yeah, so we want to take Q3 plus that. So Q3 plus 1.5 times the IQR. And that gives me an upper boundary. So what is that plus that? 65.1075. What? Is that right? Okay, sure, I'll buy that. Yep. And then we want to take Q1 and do what? We want to go to the left. Yeah, I'll draw a picture of what this means in a sec. IQR, and that's about negative 9.315-ish. Okay, so if there's anything outside of that range, it's an outlier. Do we have anything below negative 9? I have no idea what it means to have negative garbage. What would that mean? You're eating it? I don't know. We'll come back to that later. Is there anything above 65? Then there are no outliers according to the box and whisker plot. Yes, yeah, you have to do the order of operations, multiply then add. Yeah, multiply then add. Bless you. Okay, so there's no outliers according to that. Let me draw a picture of that. Let's see, can I squeeze it in up here? I think I can try. Let's use red. If this is a number line, whoa, it's a messed up number line. All right, so let's see, what's our lowest number? 18, no, minimum is 4. So if this is, what's my highest number? 51. So let's go from 0 to 51, 52-ish. What's right in between 0 and 52? 26-ish. Right about there would be 26. Right in between over here, that would be 13-ish, and that would be 39. So I want to place my numbers accordingly. So let's see. My min of 4 would be somewhere over here. Min is about 4. I'm drawing my box and whisker plot here, roughly. My Q1 is 18. So let's see. This is 26. That's 13. So 18 is going to be close to the middle here. Median is 25.7. Hey, that's pretty darn close to 26, right? There's my median. Q3 is 37. This is 39. So maybe that's right about here. So here's my box for the box and whisker. Here's my median. Here's my left number. And here is my right number just inside of 52. So the blue part is my box and whisker plot. Oh, where'd that extra squiggle come from? No idea. Crazy pen. Right? And my scale, as I just marked off 13 units, just happened to work well. 0, 13, 26, 39, 52. That's my scale. Is my scale okay? Things are equally spaced? That could be a ruler, a weird one, but it could be one. All right, so what did we calculate? We calculated the interquartile range multiplied by 1.5. So we took the distance from here to here, multiplied it by 1.5, and then threw that distance out this way, and we took that 1.5 times the distance and threw it out that way. And we found that our min and the max, as well as everything else, is in between that. So there's no outliers. Sometimes when you do that, it's going to fall right here, in which case anything over here would have been an outlier. And then you'd have to look back at the data and see. Yeah. The middle box is the median, and that's my 25.79-ish. The mean does not come into play on a box plot. A box plot is strictly percentiles. 0 percentile, 25th percentile, 50th percentile, 75th percentile, and the 100th percentile. So a box and whisker plot does not even consider the standard deviation or the mean. It's all percentiles. The min, Q1, median, Q3, and the max happen to be percentiles. Okay, so it's just a ranking picture, a picture of rank. Now what does it tell me? It tells me that 25% of the garbage lives in this region right there, and that region's way smaller than everywhere else. So there's, more households tightly packed in that region. So histogram-wise, the histogram would be taller there because it's narrower, because more people have to fit in that region. Because some guy a while ago said 1.5 is a nice number, let's multiply by it. I have no good reason for that. I have not. No one's given me a good explanation, and I haven't found one in any of my reading. Yeah. Okay, thank you. All right, what's our other way of determining outliers? And what does that have a name? Yeah. What do we call that? 2 standard deviations on either side of the mean. Kind of, yeah. The range rule of thumb. Yeah, the range rule of thumb says that you should expect about 95% of your data, most of your data, to be within 2 standard deviations, which also comes from the empirical rule. Yeah, so it's a trickle down. Based on the empirical rule, we came up with the range rule of thumb. Based on the range rule of thumb, we say most of the data was within 2 standard deviations, and so you're an outlier if you're not in there. Okay? So let's calculate that. So we need to know, we got the mean in the middle, X bar, that's my 27.854. We need to figure out how much is 2 standard deviations. So twice, that's like 26-ish, right? So this number over here is going to be X bar plus 2S. We're going to put a number over here, that's going to be X bar minus 2S. Everybody calculate that, please. Give everybody a minute to catch up to John there. What numbers you got for me, John? Anyone else coming up with similar numbers? So 27.854 times twice 12.923. Switch that with a minus. Got to definitely write X bar first. Order of operations is important. Anyone doubting those boundaries? Got a few confirmations? Okay, so is there any number below 2 in my list? No. Is there any number above 53? Okay, so there's no outliers this way either. No outliers either way. And you never know. Sometimes one will hit some outliers and the other won't. Sometimes both of them do, sometimes neither do. So no outliers here. Every data set's unique. All right, how are we doing? What's this called again, the 2 standard deviations on either side? Range rule of thumb. Range rule of thumb says about how much data is in there? About 95%. You guys are awesome. Right, yep. Yeah, right. I said if the min and max are within those boundaries, there's no outliers. Yeah, and you never know where those fall. It's possible, you know, on some other set of data that X bar plus 2S could have fallen right in between those two, in which case I'd have 1, 2, 3, 4 outliers on the right. You just got to check. How would I finally state my answer? I would have a picture pretty much looking like this, trying to figure out what I'm doing, and then I would just say there's no outliers. Oh, then I would say, yeah, I would say the following numbers are greater than, are more than 2 standard deviations from the mean, so they're outliers. And I would just list them out. Yeah. Another way to do it that's a lot more tedious is to find the z-score of every number. Anything that has a z-score greater than 2 or less than -2 is an outlier, because a z-score counts standard deviations, but that would be tedious. If I was working on Excel, that would be easy. I could just copy that formula down and boom, I could see all the outliers by their z-scores. Okay, let's try something else. What do we got here that looks like fun? Flipping a coin. I think we better do this one. Bless you. Need some tissues or anything? I'll go look for some tissues in a sec. Okay, so you flip a fair coin 3 times. The simple event is the number of heads. And then we have a whole bunch of different questions. What is the probability of getting a head followed by a tail followed by a head? What's the probability of no heads, 1 head, 2 head, 3 head? So before, I could draw a tree here. Question? You want to draw the tree? All right. Is this a binomial problem also, though? Why? What's that? Not every counting problem is binomial, though. Yeah, so just that involves counting isn't enough. So I need to meet a few conditions. Nope, it's not that it's looking for just one answer. So to be a binomial problem, you have to be repeating some experiment over and over. It's got to be the same experiment each time. Previous experiments can't affect later experiments, and the probability is going to be the same all the time. So does flipping a coin once affect what happens the second time? Nope. We're flipping the same coin over and over again, right? And is it always 50% probability of getting ahead? If it's a fair coin, yeah. So those are the 3 conditions that say this is a binomial problem. Okay, so we could use binomial stuff, or we could draw a tree. Sean wants to draw a tree. So, come on up. All right, well, he draws that. I'm going to look for some tissues for him.
Chance of getting either one of those. So you got 2 possibilities from this one and also from this one. Gary, how do you do this? Just go on. Just all right. This is a T, guys. Right there. He's trying to erase it.
This is the closest I can come to tissue. So the eraser is this spot right there.
And back to pen.
Pen back to pen, yeah.
Which one is that?
Right above the eraser.
Is it? Okay. There you go. All right, and then you're gonna have two other possibilities coming from each one of these, because obviously 50% chance of getting heads or tails.
I just want this for you.
Go ahead, Secretariat, come on. Start from the back.
All right, and we're gonna. Oh,
It takes some getting used to right in here.
yeah, I don't like it. It's weird. Okay. So it's like we flipped the coin 3 times, right?
Yep, that's it.
So that's the 3 possibilities of getting
Yeah,
them.
first flip, second flip, third flip, and
Yep.
then
And then write
you
it out.
followed to see what happens. You don't need to write all the possibilities out.
What is the question?
The first question is, what is the probability of getting a head followed by a tail followed by a head?
Probably getting no heads.
Head, tail, head.
Oh,
Which branch has head, tail, head? 1, 2, 3 of them?
head, tail, head. Yeah.
So we can switch here to the highlighter, and then you can trace that branch. Head, tail, head. Yeah, that's the only branch that does exactly that order. How many possible N branches are there? 8. So the probability of question number 1 is 1/8. You guys are awesome. Thank you very much.
I'll be here all week.
My lovely assistant, Sean. Big hand. Okay. Yeah, so there's 8, right? Because, and remember the fundamental law of counting we talked about a while ago? We have 2 possibilities, followed by 2 possibilities, followed by 2 possibilities, which gives me 8 total possibilities. That tells me how many there are. The tree tells me exactly what each one is. Okay. Now the binomial calculations can't distinguish head, tail, head from head, head, tail. All the binomial says is there's 2 heads in each of those. Okay. So next question, what was the probability of getting no heads? How many branches on this tree have no heads in them? Yeah, just that last one, right? So the next question, yeah, probability of no heads is 1/8. Control C. I wonder if I can pull this highlighter out. Let's try this. Yeah, bye-bye. Okay, what's the probability of getting exactly 1 head? Let's see, so that happens right here, right? Head, tail, tail. And then we've got tail, head, tail there, and tail, tail, head. So there's 3 ways that can happen. So if I just wrote that out here, exactly 1 head, yeah. So the probability of 1 head, we found that there's 3 ways in our picture that can happen over 8. So that'd be the probability there. Exactly 2 heads. Let's do highlight that in blue maybe. Let's see, that's the first one, right? And this last one had 2 heads in it. And the first one on this bottom branch has exactly 2 heads. Any other ones? So probability of 2 heads is also 3/8. And let's see, the probability that all 3 are heads. There's only 1 way that can happen. Yeah. And that is this branch right there. Probability of, so I'm going to write this just a little bit different for a minute. I'm going to summarize what we just did in a table. So that'd be problems what? B, C, and D, and E. Oh shit, I hate when that happens. I'm going to skip part A in my table. And so what I'm going to do is I'm going to count heads on this side. So count heads. And I started off counting and said there were 0 heads. And on this side I'm going to write the probability. There was a what, 1/8 chance of that happening? And then we looked at having exactly 1 head out of 3. Probability was what, 3/8? Probability of 2 heads, 3/8. Probability of 3 heads. 1 head. Are there any other way to get heads besides 0, 1, 2, or 3 in this scenario? Those are all the possible outcomes, simple outcomes. Is this a probability distribution? Yes. It adds up to 1. What adds up to 1? The probabilities add up to 1. Yeah, the sum here of the p's is 1. Is this a probability distribution? And the answer is a big fat yes, because of that. Even better, this particular kind of probability distribution is called a binomial distribution. In which case, we could use the binomial formula. Now, I'm not going to make you write it like I did on the last test, but who thinks they remember the binomial formula for a single event? Who? You want to give it a shot? So the probability of getting a particular one of those x's, you think it's n factorial? Yeah. X factorial, yeah, feel free to help him out. Parentheses n minus x, factorial, okay. Yeah. N minus x, yes, matching what I see down there. You could draw a tree instead. Or you could push a button on your calculator. What button on the what function on the calculator does the same thing? What was that? Almost. PDF. This is the binomial PDF. Binom PDF. NPX on the calculator. Excel has one too. I think it's called binom dist, and it's XNP, I think. Slightly different order. Okay, what's P and Q? Yeah, so P is the probability of a success. And Q is a failure, which we could say is 1 minus P. So we could be counting heads. We could be counting having girl children. That's a success. A boy is a failure. Just kidding. Okay. Depends how you look at it. A PDF just finds a single value. CDF would be, let's see, new page. So the binom CDF for NPX would be the probability of being less than whatever that X value was. Or less than or equal to, sorry. Well, that would be a right tail. So if you were looking at this distribution, it might look like this. Say that's the distribution right there, and X is right there. What the CDF would calculate would be the sum of this column, this column, this column, this column, this column, and that column. That's what the CDF does. It does left tails on the distribution. What would we do for a right tail? Yeah, sort of. I'll draw a picture of that next. What's that? So this would be a situation where I want at most X, like I want at most 3 out of 7 boys in my family, right? Something like that. All right, so that look, what the hell is that supposed to be an L there? All right, suppose I wanted a right tail binomial. So that would be something like the probability of being greater than or equal to whatever X is. So picture-wise, if I drew a similar distribution, something like that right there. And let's say X is right here again. I would want to know this stack, this stack, this stack, and this stack. So to calculate that on the calculator, that would be 1 minus binom CDF NP no. If I did that, it would subtract, if I put an X there, it would subtract this column and everything else. But I want to keep that column. So if this is X, what would this guy be? It'd be X minus 1 is the column right before it. Yeah, so that would have to be an X minus 1 there for this to work. Yeah, that's the tricky one. Right tails are hard with binomials. This would be, I want at most, at least X, sorry. At least. So I need at least $10 to go to the movie tonight, Dad. Come on. Right? That means she wants $10 or more. Say that again. 1 minus, correct. Yep. Yep. Only if you're doing the 1 minus. Yeah. Because what you want to do is you want to eliminate this column, this column, this column, this column, and this column, and that's what the minus is doing there for you. And you just have to start one place lower to make that happen. Yeah. There's like professional statistical packages. If you type binomial and then you give it an X value, it will spit out less than X, less than or equal to X, X, greater than X, greater than or equal to X. And so you can look at them all and just pick the one you want, which is kind of nice. The left tail would be like at most, I want at most 3 boys on this basketball team, something like that. And that would mean I can have 3, I can have 2, I can have 1, but I can't have 4 or 5 or 6. No. So in a case like that, I'm saying X is 3. Yeah. Yeah, P is the probability of a success, whatever that means, like 50% chance of picking a boy, or maybe 30% chance of getting a green P or something like that. Yeah. All right, let's do another one. I think we beat that one to death. Oh, this is a good one. A female student scores 80% on a math test that has a mean of 86.81 and a standard deviation of 17.71. That's all for females. On the male side of the test, her male friend got 80, but the males had a mean score of 88.62 and a standard deviation of 15.51. Relative to their peer male and female students, who did better? We're not going to do intervals here. This is just compare their z-scores. Yeah, we're just going to compare z-scores here, yeah. So with respect to their peers. Other thing we could do is do percentile rank. The problem with that is I need the whole data set to do that. So I can't do that. Since I'm only given a summary in terms of mean and standard deviation, my only way to compare them is z-score. So find the z-score for the female group, find the z-score for the male group. I'm going to copy that into my notebook here. If I had the whole data set, I could do other things to compare. But based on only those numbers, the only thing I can think to do is z-scores. So for the female, so I'm going to put a z with a little f for female. That would be her score minus the mean score over 17.81. And we want to compare that to the males. 80 minus, bless you, 88.62 divided by 15.51. And remember, whenever we have complicated fractions, we have to put parentheses around the complicated parts in order for it to come out right, or do it in stages. Anybody get a male or a female z-score? Somebody besides John? Kyle, calculating? Oh, why didn't you say so? I got one here. Don't want you to miss out on all this fun. Which one? Males? Negative 0.556. And you got a female too?
Yeah, -0.3824.
Okay. Now, what do I always do with problems involving z's and normals and stuff? I draw a picture. So I'm going to draw a picture just to get a feel for what the hell's going on. Z-score center is 0. And let's say they're both negative, so -1 is somewhere over there. And so the male student is about right here. And the female student compared to their peers. Now, granted, they both got an 80, right? So this is just z-score comparison. So maybe I should use a different, I'm just going to throw it here anyway. The female student, she has a z-score of about right here compared to her peers, females. So compared to their peers, who did better? The female is closer to the mean. She's further to the right, right? So the female did better compared to her peers than the male compared to his peers. The male is much more below average than the female is. This would be another way to state that. Does that make sense? Relative to their peers, the male is more below average than the female is. So who did better? The female did better with the score of an 80, is what my conclusion is here. They're both below average, as the male is further below the male average and the female is below the female average. Yeah. What? I'm going to twist this on you now. What if they each got a 90 instead? Refigure their z-scores. Get a clean, oops, wrong data, crap. So Z sub male, 90 minus 86.81 over 17.81. Oh, crap. Thank you. Got my males and females backwards. All right, we got z-scores. Female. And the male.
0.0889.
Agreement? Yeah? Okay. So I'm going to draw a number line again. So I'm trying to figure out who did better compared to the peers. A z-score of 0 is there. And the female, let's say that's about 17.179. So that's female. And male is way over here. Who did better here? Female. She scored more above average, which is good. She's further to the right. New question. Which data set is more spread out? Why? Oh, no, in general, right? So forget about this for a minute. Forget about the 90. Which data set is more spread out, the males or the females? Females, because are their means the same? Then their standard deviations are not comparable if the means aren't the same. What do we do to put them on equal footing, to compare spread? What? Find the mean of everybody? Maybe. I don't know about that. I'll have to think about that. There's a little part of my brain that's saying, no, that doesn't work. No, that's what he said. Yeah, and that's that. I'm not sure about that. Coefficient of variation. Anybody remember that? Coefficient of variation gives the standard deviation as a percent of the mean. So to find the coefficient of variation, I usually call that CV, you take the standard deviation and divide by the mean. So do that for each of these. Find the coefficient of variation for females and males. No, what it does is it allows us to compare their standard deviations, because you can only compare standard deviations if the means are identical. If they're not identical, you have to do this one right here. So what do we got? 17.81, 86.81. Versus 15.51, 88.62. So to the nearest tenth of a percent, can you give me these? So 3 decimal places as a point. So it's 17.5. Male, 17.5. And females, what is it? 20.5. Yeah. So based on they have different centers, the female still has a bigger spread. But you can't compare the standard deviations directly if the means aren't the same. You got to use what's called the coefficient of variation. It's not. There's no button for that on the calculator. No, you just have to do it. So it's coefficients of variation. And that's the way you compare standard deviations from 2 different groups to see if they're different. All right. Let's do another one. How about yeah, let's do the next one. According to the U.S. Census Bureau, about 17% of adult Americans have bachelor's degrees. I think we're trying to up that to what now? Has anyone heard what the goal is for the United States? I think it's 40%. Yeah, it seems kind of wild, huh? Yeah, and we want high school graduation to be 100%. Right now in Oregon, it's like, what is it, 70% maybe? Or is that just in Portland? It's not high. Okay, anyway, we have a sample of 100. Is finding 20 or more with a bachelor's degree unlikely? I used the word unlikely there. What word do we usually use? Unusual, right? Okay, so we have to think about unlikely versus unusual. How do we determine if something is unusual? If what is less than or 5%? So first of all, is 20 below or above 17%? 20 out of 100 is 20%, it's above. So the question here, I would ask, another way I could ask this question is, whoa, what the hell happened? Oh, that's not my whiteboard. Haha, I knew that. Is 20 an unusually high percentage, usually high number of graduates, unusually high number of graduates, if what is expected? If 17 is expected, 17 out of 100, 17% of 100 would be 17, is expected. So that'd be another way to phrase this question. So expected, there we go. So whenever we're talking about unusual events, we have to explore a tail. So my distribution might look something like this here with a long right tail. I'm expecting to have 17. I found 20. So I need to find the right tail on this point since 20 is above the mean. Okay? Yeah, so this would be 1 minus a binomial. Right, Joe? 1 minus the binom CDF, because I'm trying to find the probability that x is greater than or equal to 20 here. And then n is 100. P is 17%, 0.17. What's x going to be here? 19. You are wonderful today, Alan. Good job. That should be the calculation we want. Yep, that's the x minus 1. Anybody got a number on that? .248, so about 24.8%. Is that less than 5%? No, so it's not unusually high. It's close enough to 17 to say, hey, yeah, that's, you know, it's not too far from 17. Okay, now comes the sketchy part. What is unlikely? I didn't use the word unusual here. I used unlikely. What does unlikely mean to you? Like, did we ever define unlikely anywhere in the book? Oh, we never defined that. So now it's a matter of personal opinion. Is 24.8% a small enough probability that you would say it's unlikely to happen, or it happens like 25% of the time? That's not unlikely. It's not really likely, but it's not unlikely either. It's just in this fuzzy zone in between, right? But it's not unusual, is it? We do have a definition for unusual. Unusual is the tail probability is less than 5. That is definitely greater than 5. So this is not unusual, but I wouldn't say it's unlikely either. It's not really likely either. It's just 24.8%. It's not unusual. It's not really likely. It's not really unlikely. It's 24.8% chance that this happens if 17 is expected. It's 20 is not really likely. Like something's likely to happen if, you know, I have a really loose likely, like if it's more than 50%, it's kind of likely to happen, right? If it's likely to rain, if the probability is more than 50%, I'm going to probably bring a raincoat or umbrella if I don't want to get wet. So 20 is not really likely, and it's not really unlikely either. Oops, wrong order. Unlikely. So we found the probability of 20 or more graduates out of 100 is about 24.8%. But it definitely doesn't meet our criteria for unusual. That we have defined. We don't have likely and unlikely defined. They're vague words. All right. We got time for one more problem. Let's see. We just did. Yeah, so this is very likely to happen on the test. I will have a problem later that refers to the data in the beginning. So this number 6 says in problem 1, weights of garbage are given. So in order to solve this problem, you have to look back at that data to figure out what's going on here. No, not at all. Because to do a confidence interval, all you need is the summary statistics, which I gave to you. But you have to remember to look back there. But I guarantee somebody in the room will say, hey, where the hell's the mean here? And I'll say, hey, it's on page 1. That's okay. It's not test, it's pressure, right? It's okay to forget little things like that. Okay, let's see, we got 10, we got 11. Let's do 11. Okay, a statistician read that the percent of adults in the United States who use cell phones while driving is 75%. To test this claim, the statistician selected 63 people and found that 55 of them drove an automobile while using a cell phone. We're assuming the statistician made a random sample of some sort. Okay, that's important. Although 63 is greater than what critical number here? 30, yeah, so we're okay either way. With a significance level of 2%, test the claim that the percent of adults in the United States who use cell phones while driving is greater than 75%. So if he's going for a greater than, that means the data must have convinced him to head that direction. Because otherwise, what's the safe thing to do with hypothesis tests? Not equals the safe thing, a two-tail. Yeah, so first thing I'd like you to do is state the null and the alternative hypothesis, and then we're going to draw a pretty picture, and then we'll plug some stuff into the calculator and make a conclusion. All right. What's the null here? That the proportion P, this is a proportion, right, not a mean, the proportion P is 75%, and the alternative is greater than. Excellent. Yes, yes, yes. All right, so notebook, new page. So H0 is that the population proportion P is equal to 75%. I'm going to write it as 0.75. And my alternative hypothesis, H1 or HA, is that P is greater than 0.75. And what's my alpha here? 2%. Yeah, so 0.02. Okay, so draw a picture of this scenario. Draw your best normal wiggly curve. No, you don't. All right. Am I doing Z's or T's here? Z's go with proportions, correct. So Z equals 0 is in the middle. Where does my 2% go? Right tail. No, just the right tail here. Are you messing with me? Oh, good. Okay, so that is the shaded area, correct? The 2% is the shaded area. Oops, 2% there. What would be to the left of that? Yeah, so that's like having a 98% confidence level of something happening. Okay. All right. So we could calculate that z-score if we wanted to. That is called the, let's see, is the critical value maybe? Inverse norm, yeah. Okay, so what is the inverse norm? What would I plug into the inverse norm here? 0.02. And that spits out -2. Holy shit, that's on the wrong side. We need to call it 2. Yeah, if we wanted the exact right number, we would have done 1 minus 2%, 98%. Inverse norm only does left tails, right? So if you do this, you can have the wrong sign. So I'm just going to put a little negative in front of it. And so my answer is about, what was it again, Sean? 2.05. Okay, everyone okay with the 2.05? Yeah, and notice I put z equals 0 because I remind myself positive z's are on one side, negatives are on the other. Null hypothesis is in the center too. So if I went with proportions in my scale, 0.75 is the same as a z-score of 0 here. All right, what function on the calculator are we going to use for this right here? To test the hypothesis. 1 prop z test. Correct. This is a test. 1 prop z test. So run your 1 prop z test. See what you get. I'll run it too. What was it? The numbers again? 55 and oops, where'd it go? 55 out of 63 people. Yeah. Oh, sweet. It is a right tail, so it's greater than, correct. Oops, that's up there. No, it's not. Where the hell is that? Oh, right there. One prop Z test. There's so many of these and they all kind of look alike. I always have to be really sure I'm picking the right one. Okay, so P sub 0, that's the null hypothesis, 0.75. X we found was 55. N was 63. And we are doing a right tail. How am I doing? Pretty good? Calculate. Okay, so we found the Z-score is negative 12? Oh, shit. Yeah. Negative. I don't think I've ever in my life seen, oh, once I've seen a Z-score that big, but it was wrong. Okay. One proportion Z test. Oh, answer key. Yeah, that's mine. Thank you. Oh, yeah, it's fine. Anybody want an answer key? Oh, your hand went up first. Good job. I'll post these after class. I didn't post this answer key yet. One prop Z test, right? Yeah, that looks right. 0.75. Oh, 5. I typed 5. Crap. 55. All right, that'll be better. Ah, there we go. So about 2.25. And my p-value is about 1.2%. That's relatively little. Does it fall below my significance level? What was my significance level? 2%? Yeah, and that's less than 2%. So are we going to reject the null? No, we don't know. Yeah, yes, no, maybe. Uh-oh. We are. Oh, wrong button. Oh, what did I do? Holy shit. Escape? Ah, escape's a nice button. So what was it? So the Z-score? 2.25-ish? So if the red mark is 2.05, 2.25 might be right about here. So that's my test statistic, 2.25. Test statistic. And the area to the right of that test statistic we found is what? That's called the p-value. Yeah, so about 1.2%. And that is less than 2%, our significance level, so then we get to reject the null here. Okay, so the null says the mean is 0.75. We get to accept the alternative that more than 75% of drivers use their cell phone while driving, according to this data. What's our p-value again? 0.12 or 1.2%. And in a lot of studies these days, they skip over the critical region and the critical value, and they just go right to the p-value often. They said, here's my data, my p-value was 1.2%, and then you decide if you think that's significant or not. They'll all make their decision too. They'll say, I think it's significant or I don't because of whatever. All right, we're out of time for fun with statistics. I will post the answer key for this. On Monday, there will be a similar test to this one. I would like to make it shorter, but I'm not sure I can do that, but we'll see. This was the second one I posted. What? It's going to be about 10 or 12 questions, yeah. I'm not going to record any more of those problems, but I will post all of my answers to this test. Test is 8 a.m. on Monday. Yeah.